Okay, so this is 2016 paper, question 2b. Assuming that the portal frame in figure Q2, which is this here, is fully fixed to the ground and all its structural elements have the same cross-section. Part I, sketch all possible collapse mechanisms. So the approach we're going to take is using the Williams and Todd book. What I've done is I have labeled each of the corners and where there are applied loads with letters for ease of calculation. So in order to sketch all possible collapse mechanisms, the first thing we need to do is to find out how many possible collapse mechanisms. Now the process that I'm going through is specifically for frames, so you would use a different method for beams, which should be covered in another video. Okay, so step 1, check number of possible mechanisms. Okay, now the way to do this is first you calculate the degree of indeterminacy, which I will call DOI. Now we can use the formula 3m plus r minus 3n, right, where m denotes members, r denotes reactions, and n denotes the number of joints. Okay, so let's flip back. Okay, so how many members do we have? Well, we have 2 vertical members and 1 single horizontal member. So we know that we're going to have 3 multiplied by 3 plus the number of reactions. Okay, so we only have 2 reactions here. We have 2 fixed supports. Each fixed support has obviously a vertical, horizontal, and a moment there. So we'll have a total of 3 plus 3, which is 6. So we're going to have 6 reactions minus the number of joints. So this is 3 lots of. So this is, when we say joints, let's not confuse it with hinges. Joints are basically what connect members, right? So that at the either end of members. So in this scenario, we're going to have 1 joint here, 1 joint here, 1 joint here, and 1 joint here. Now that's not a hinge. A hinge is a completely separate. It's a completely separate concept. These are joints. So these are things that split up elements. And we have 4. So we end up with 3 times 3, 9, plus 6 gives you 15, minus 12. So 15 minus 12 equals 3. So we have a degree of indeterminacy of 3. Right? Okay. Next thing to do is to determine the number of possible hinges. So possible hinge positions. So now we are talking about hinges, right? So we're going to label that as P. Okay, so if we to draw a small sketch of our scenario, now we have to think about where hinges usually form. Now hinges obviously form when there is sort of max moment areas. For this scenario, because we have a load being applied like this, and a load being applied like this, you would suspect that there would obviously be a pin generating here. I'll do that. So let me remove the forces now. So you'll suspect a hinge forming here where that load is being applied, a hinge forming there as well, and you would suspect hinges to form on all other joints. Why? Because this is a fixed, the base are fixed supports, so they will generate a moment. If you were to do a bending moment diagram, you would have some value at your fixed support, accounting for the moments within the system. And you would have them at joints, because obviously bending moments transfer across joints. So if you had something like this, if you had something like this, so you generate a moment here, and you also generate a moment here. So that's the likeliness of those causing or creating plastic hinges first. So let's remove that. Okay, so we come up with 5 possible positions of plastic hinges. We're going to say P equals 5. Now we are going to determine the number of independent mechanisms. So the number of independent mechanisms, right? So what do I mean by that? What I mean by is how many mechanisms can we create within the system separately, so not happening at the same time. And the way you calculate that is P, which is the possible hinge positions, minus your DOI. So that's 5 minus 3, that equals 2. So you end up with 2. And we'll go further into these different mechanisms. So generally we know that this comprises of either a beam mechanism or a sway mechanism within the frame, right? And we'll go into more detail as to what a beam mechanism looks like and what a sway mechanism looks like. Now, the total number of mechanisms would be, so if we were to call this, okay, just making some space. So the total number of, possible mechanisms, let's just say mech, is equal to the number of independent mechanisms, which is 2, plus 1. Why plus 1? So that's going to equal 3. Why plus 1? Because you can have a combination of a beam and a sway mechanism at the same time, and that's completely that's a completely different mechanism on its own, different to just a beam mechanism or a sway mechanism. But that is a beam plus sway. Okay. Alright, so now that we have now we know the number of mechanisms that we're expecting, which is 3, we can start to sketch these possible mechanisms. So the first mechanism we have is a beam mechanism, and this generates when you have hinges forming in the top right corner of your frame and the top left corner of your frame, and a hinge, a plastic hinge, where your point load acts. So we get this sort of failure / mechanism. Let's draw that straight. Alright, so this is what the beam mechanism looks like. So you've generated, so this is where your force point load is acting. You've generated hinges on each of the top corners and one at just under the point load, right? Because this is where you're most likely to incur large bending moments, and so your plastic hinge will form here first. Right, so this type of mechanism is called a beam mechanism. Notice how it's only three hinges, yet it's caused a beam mechanism. Okay, next one is a sway mechanism. Now this is when you develop plastic hinges at each of your joints. So top left, top right, bottom left, bottom left, bottom right. And so this causes your structure to sway. And so the way your structure will sway is something like this. So your structure sways like this, right? With some angle theta, them being the same, because of that failure. But the angle is not necessarily important in demonstrating the type of mechanism that it will produce. So far you have a beam mechanism and you have a sway mechanism with plastic hinges in positions, but all within the 5 possible locations of where a plastic hinge can form, as we discussed earlier in step 1. Okay, finally we end up with a combined mechanism, which is what we discussed before. Now a combined mechanism is an interesting one. When your beam, this is when your portal frame fails as a beam mechanism and as a sway mechanism. And that happens when you generate plastic hinges in your 2 supports, and you generate a plastic hinge here in this. You generate a plastic hinge here in this top right corner, and one under the load. Let's show that as there within the structure. And so what you end up with is something that deforms like this. So let's and so your hinges, your new positions of your hinges appear like that. So that is both a combined beam. It's called a combined beam and sway mechanism. Okay, so I mean generally what you could do as a drawing here is just show the new positions of the hinges. So you wouldn't necessarily have to draw on the existing structure. So your hinges form here. So that is going like that. That is, or you could say, is traveling like that. And that is traveling like that. That's just how your hinges move. Perhaps I may have confused it. What I'll do is I'll do it again. Okay, so let's draw our frame. So here is your portal frame. What will happen is you'll generate hinges here, 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 and here, and so you end up with a mechanism that looks something like that. That's your sway slash beam. So and for the previous one it will sway like that, and if you want to show where this hinge is actually formed on the frame. Show it like this, and then you can show the deflected shape. So basically what's in red is the deflected shape. So that's just a beam mechanism, so it will look something like this. So your mechanism deflects like that. Obviously that's failure. You don't want to be in a building that's, you know, failed like this. But basically that's all you had to do for part I. That's what is expected from you in part I. In terms of resources, you can look at page 362, and it goes into detail of, so this is of Williams and Todd. It goes into detail if you want to know more about this, but this is basically the gist. So step 1 is you want to know how many mechanisms you have first in order to sketch all possible collapse mechanisms. The way we did that is first we checked the number of possible mechanisms by calculating the DOI using this formula here. Then we calculated the possible hinge positions. That's quite, comes with experience. You'll have an idea as to where hinge positions usually form, but you won't necessarily, for example, put a hinge here if there is no point load, if there's no load acting there. So we only put one in the mid span or along the span here because there is an applied load there, but otherwise we wouldn't have put it as a possible hinge position. So let's So once we've done that, we then identify the number of independent mechanisms by subtracting the possible hinge positions minus the DOI. That gives you 2, and then you add the total number of mechanisms is 2 plus 1, because you can have a combination of a beam and sway, which, as we showed here, this is a beam mechanism, this is a sway mechanism, and a combined mechanism. So if you want to know more about this, you can see it in page 360 of Williams and Todd.